In this video, we're going to go through linear transformations, and this will be a long video. There are 14 slides, so just bear with me. So we know from our vector spaces sections that vectors are polynomials or matrices or continuous functions or other types of mathematical objects. In this, we are now going to extend that definition into linear transformations, and we're going to talk about domains and codomains. So we're going to let T be defined as a transformation that takes vectors from the entries that are in the complex with m entries, and it's going to do something to map it to it, or some kind of function is going to happen so that it now has the final result, or the output would be the vectors with complex numbers with n number of entries. So we're going to denote T as being the function, or it's going to do the mapping. It's going to transform one into another. Cm is our input, and it's going to produce the vectors in Cn, and we're going to call that the output. Another way we're going to say the domain of T is Cm, that's what's going to go in, and the codomain is Cn, that's what comes out. Then for every vector u in Cm, the vector Tu is called the image of u under T, where this is representing the output. So this is the output. The image of u under T is the output, or the codomain. The set of all the images of u in Cm are T are called the range of T, denoted as R of T, and thus the range of T is a subset of the codomain of T. What that means is that you may have elements in the codomain that are not going to have a pre-image. In other words, it's not going to have an input associated to it from the domain. So let's see what we mean by a linear transformation. A linear transformation, let's do this again. A linear transformation, where we say T is a linear transformation of u into v, is a function that carries the elements, or we may say it maps the elements of the vector u into the domain to the vector space v called the codomain, and it has to have these two properties. That we have to have closure for the addition, so I can either first add the two vectors in u and then do the transformation, or I can do the transformation individually, and it'll also end up, these u1 and u2 will be from u, and the transformation tu1 and tu2 will end up in the codomain. Also, we have the scalar multiplication, so I can multiply the scalar times the u vector first and then do the transformation, or I can do the transformation on u and multiply it by that scalar. And that's going to hold true for every single u vector in my domain, and it should end up with being a scalar times my range, or my scalar times my domain, and then I can do the transformation, which should still end up in my domain. One of the things that has to happen is for linear transformation, we take 0 to 0. So suppose we have this linear transformation. Then when I put 0 in as my vector, the transformation is going to produce 0 out. So this is going to be important later. This means when you put in the 0 vector, the zero vector had better come out. So it's something to think about when we get further into it. So here's some diagrams that we're going to look at. One of the diagrams we're going to look at is, if we think about that, we're going to start with u1 and u2. Then we're going to perform some transformation on it. And so I have the transformation of u1, u2. Now u1 and u2 are coming from the domain. When I do the transformation, they end up in the codomain. And I can either do the addition before, so I can go this way and do the addition for and then do the transformation, or I can do the transformation first individually and then add those two. When you think about it, this was when we were learning about the algebra of functions in our pre-calculus 1 class. Remember when we had the pre-calculus, we had the algebra of functions, and we defined that we had this function f of x, and then we had this function g of x, and we could do it that way, or we could do f plus g of x. Well, this allows us to actually have done this in pre-calculus 1. So let's keep moving. Now, if we think about it with the transformations, with the scalar multiplication, I can take my u vector and multiply it by my scalar first and then do the transformation. Or I can do the transformation and then multiply it by that scalar. Again, if we think about when we had the algebra functions and we had our a and f of x, we could have done it that way, or I could have done f of a of x. So nice scalar transformations goes back to explaining why we were able to do some of the things that we did in our Pre-Calculus 1 class. Now here's another way of looking at our transformations, our linear transformations. Here is all of, well, this is some vectors, not all the vectors. Here are some vectors that are in my domain, and then I do this mapping, or I do this linear transformation, if you will, into my codomain. Now I'm realizing, of course, that I can have leftover elements in my codomain that are not being mapped to by a element in my domain. But every element in my domain does need to be mapped to one element in my codomain, but I can have leftover elements in my codomain that are not, they don't have a pre-image, if you will, in my domain. So that's something to think about, and we'll explore this further in our next couple of sections. So let's just take a look at a nice transformation here. So we're going to let A be this matrix where I have 3, -8, and 5 in the diagonal. And I'm going to define my linear transformation from my entries in R3 back into R3 by A multiplied by my A matrix here multiplied by my vectors X, where X are coming from my first R3. And when I get done with this transformation, my vectors will again be in R3. So we're going to find the images. That is, in other words, when we're talking about images from up above, we know this is like finding the codomain, or if you want to think about it as in terms of when we're back in Pre-Calculus 1, we called them our range. So these are our codomains. When we talk about the image, it is the codomain values that we're looking for. So let's scroll up here. So suppose we have these vectors that are initially in our domain u and v. Here's my u and here's my v. And then let's go ahead and do that transformation. So in other words, I'm going to take these entries in this matrix, and I'm going to do my usual matrix multiplication the way I defined it. So I'm going to take this u and multiply by this A matrix, and I get this. And I'm going to take this V matrix and multiply it by this A matrix, and make sure we pay attention to the order. Order does matter with matrix multiplication. And what we're doing is we are just finding the codomain values associated to the domain values of u and v. We're not trying to prove it's a linear transformation. So we're just kind of getting used to, hey, look, this is how we're going to define a linear transformation. Let's find the codomain, or the images. So just getting used to some of the notations and what it means. Here's another one in which we want to actually show this as a linear transformation. So we're going to have entries in R2, and I want to end up in this polynomial of size 2. So that's what the linear transformation is. And so I have a vector that's in R2. That means I have real entries, and I have 2 entries in that vector. And I end up with a polynomial of degree 2. And this is how I'm going to define it. I'm going to take my first entry, multiply by x squared, and then I'm going to take my first entry, subtracting my second entry, multiplying it by an x, and then of course subtracting off my second entry. This ensures that this is going to be a P2 or less. Now remember, P2 means polynomials of degree 2 or less. So to show it's a linear transformation, let's go ahead and just start out with the fact that if I have 2 vectors from my R2, that I should be able to add them first and then do the transformation, and I should get the exact same answer as if I would have done the transformations of each one individually. So here's some generic A1, A2, B1, B2, and I can add these entry by entry, so A1 and B1, A2 and B2. Now if I apply this transformation, this is my first entry. So because this is my first entry, here's my first entry here, which is this. And then my second is my second term is going to be my first entry, which is again the same first entry here. And then I'm going to subtract off my second entry, which is this one. And then, of course, I'm going to multiply it by that x. So there's my second entry. And then I'm going to subtract off my second entry. So there you have it. So that is just going through the addition and then applying the transformation. Now, if we reorder it by putting all the a sub 1s and a sub 2s together and all the b sub 1s and the b sub 2s together, doing the usual distributions and combining up like terms, you can see by the way that we defined my linear transformation of a1x2, a1 minus a2 times x, and then subtracting a2. Here is the transformation on a, and then here is the transformation on b. So we have shown that we can add them first together, or we could have done it individually first, and I would have gotten the same answer. So now we have to check the second criteria, and the second criteria is multiplying by some scalar c. So c is my scalar, and I have to be able to multiply my scalar into my vector and get the exact same things if I would have had my scalar after I multiply my scalar after I've done my transformation. So again, I'm going to have a1 and a2, and so here is c of a1 and then c of a1, c of a2, minus c of a, and of course I have my x squared, my x, and you can see that I can factor c out of every single one of those terms, so I get the fact that it is the second condition is met, therefore it is a linear transformation. Now let's take a look at another example and determine if this is a linear transformation. So here's my transformation. I'm going to go with complex numbers into 3 entries and back into complex numbers with 3 entries, and this is how I'm going to define it. So let's see if it holds for addition. So I'm going to choose 2 vectors, x and y, where I have x sub 1 to x sub 3 and y sub 1 to y sub 3. And I get the usual addition of vectors, so entry by entry. Now if I apply my transformation, I'm going to get 4 multiplied by my first term. Again, here is my first term. So 4 multiplied by my first term. And of course, I'm going to have my first term down here. You can see that. And then I'm going to have my second term, and it's going to be 2 times my second term. So here's my second term. And then, of course, I have my last one, which is 3 times my third term. Here's my third term, and 3 times my third term. Now, if I do my usual breaking apart so that I can put all my x sub 1s that do in the distribution and putting my x's together and my y's together, what I end up with is this. The first part kind of holds. I get the first entry, I get the second entry, but I do not get the third entry on either one of them. And in fact, this is what I get at in my third to get that -2. So I know that S is not a linear transformation because I can't add the 2 vectors first and then do the transformation to get the exact same answer as if I would have done the transformation on each vector individually and then added those 2 answers. So this is an example in which this is not a linear transformation. Let's take a look at my next example. We're going to define the linear transformation as a polynomial of degree 3 or less, and it's going to be transformed into a 2 by 2 matrix. The way I'm going to define it is that I have the constant and the coefficient on the x term are going to be added together in the first position of the matrix. I'm going to have the coefficient on the x squared term, that's going to be my c, so a minus 2c, and then of course here's my d, that is the coefficient on my x cubed term, and here's how I'm going to define this. And this should look vaguely familiar, and so let's see if this is a linear transformation. First thing I'm going to do is check for the addition, so if I add the 2 vectors first, and I'm going to just use a1, b1, c1, d1, and then a2, b2, c2, d2, just because I'm going to just use the a, b, c's, d's as I did before, but I'm just going to subscript it. It'll make it a little bit easier. And you can see that I'm going to put my a2s and my a1s together, my b1s and my b2s, and etc. And I see that that holds for the first condition. I'm going to check to see if it holds for the second condition. I have some alpha, and again, my x is going to be a, b, c, and d. I don't have to subscript this, because I'm only working with one vector. Up here I had two vectors, so I did have to work with the two vectors. And you can see that this is also going to hold for the multiplication by the scalar. So this is a linear transformation. So let's define some linear transformations of addition. So I have this linear transformation T. I have this linear transformation S. We have the same domain U on both of them, and we have the same codomain V on both of them, which means what I can do is I can do the addition of those linear transformations and then apply it from U mapped into V, or I can do them individually and then add those two answers together. That leads us to, of course, some theorems. We always have theorems. So this theorem says, if this happens, if I have T and S are two linear transformations with the same domains and codomains, then the T plus S is also a linear transformation. We're going to define linear transformation with scalar multiplication. So of course, suppose T is a linear transformation and alpha is a scalar, then the scalar multiple is also a linear transformation. Get a couple of more theorems here because, we've got to have these theorems in here. So our next theorem is multiple of a linear transformation is a linear transformation. So, I think we just talked about that one. No, this is the theorem that matches that definition. Apologize for that. Which then gives us this next one, which has this multiple. So we have these linear transformations, U1, U2, U all the way to UT. Those are coming from our domain, are the vectors from U. And then we have these scalars. So I can apply individual scalars to each one of those vectors, and that also will be a linear transformation. Let's look at another example where I'm going from a polynomial of degree 2 into a polynomial of degree 4. Or less, and the way I'm going to define that is my transformation is my polynomial of degree 2. If I multiply it by x squared, I'm going to get a polynomial, obviously, that is going to be degree 4. I want to know if it's a linear transformation. So using the fact that I have that previous theorem right there, I'm just going to go right to the previous theorem, and I'm going to say, okay, I've got C1 and C2. These are both scalars. P1 and P2 are degree 2 or less. Here is I'm going to define it just like I did with this theorem, and you can see that this is going to hold, so this is a linear transformation. Now we started out with a matrix and we did some multiplication and we said, hey, this holds. Well, given a matrix, then you can build a linear transformation always. You can always do this. So let's take a look at an example where we start out with this matrix A. I'm going to define a function so that I'm going to start in R4, and then I'm going to end up in R3 so that my transformation, my P if you will, my linear transformation P of X is going to be in the multiplication of my matrix A times X. Now remember, X has to have 4 entries, and so here is my X. It has the 4 entries, and I assume X1 to X4 are real. And then this is how I'm going to define it. My matrix A multiplied by X. Now, we know that it is going to be the X sub 1 on the first column, X sub 2 on the second column, X sub 3 on the third column, X sub 4 on the fourth column, and that's just basic matrix multiplication, entry by entry. So the function takes the components of the X vectors and turns them, as you can see, into scalars. So we know that it takes it into a linear combination of the 4 columns of A, which are in R3. So we know that's going to hold true. So we know that we're taking something in R4, and then it's going to end up in R3. So that is that there. So now we just have to make sure that we have, let me just scoot this up, that this will end up in R3, so we have X sub 1, and so we have 3X sub 1, 2X sub 1, 1X sub 1, and we end up with this 3 entries adding across the rows, each entry vector addition, our usual entry by entry vector addition. So we end up with 1, 2, 3 entries, and so we know that we're going to end up in R3. So we have that. Now we just have to show that the two conditions for the linear transformations hold. And the first one is the P of x plus y. So A of x plus y doing our usual addition of matrices and vectors. We know that the matrix multiplication is going to distribute over the vector x and the vector y, which means I end up with P of x and P of y. And then, of course, with my scalar, with my usual scalar multiplication of a matrix. So therefore, we know P is a linear transformation. Formally, we get these two theorems. It says, suppose A is a m by n matrix. We define this linear transformation of some Cn into Cm by the linear transformation T of x, where it is a matrix A multiplied by x, and then T is a linear transformation. And the other one we get is the column vectors. Suppose we have this linear transformation, then there exists an m by n matrix such that we get a linear transformation. So if we were to restrict our study to just linear transformations those who have codomains and domains are both vector spaces of column vectors, every matrix leads to a linear transformation of this type, while every such linear transformation leads to a matrix. So matrices and linear transformations are fundamentally the same. We call the matrix A of the matrix representation of T. So all this time we've been working with matrices, we were really doing linear transformations. So I want to show you what it looks like if you were looking at it in terms of the xy plane. So let's define our image S, so that we're going to define S as being a unit square in R2. If I define my first linear transformation T1 of x as being this transformation, where I've got 3, 0, 0, 2 multiplied by my x, which is my pre-image, if you will, I'm going to end up with this area. And if I define my second transformation as 1, 2, 2, or 1, 2, 0, 2 times my x, where again I'm looking at my unit, this is where it goes to. Now, what's happening is it's taking these points, this point right here, which is the representation of the vector of 0, 1, and this point, which is the vector 1, 0, and also this point, which is the vector 1, 1. And it's doing that transformation. So it's taken each one of those corners. Each corner is going to be multiplied by this matrix on the right-hand side. And the same thing here. And you can see what happens to the matrix when it's being, each one of these vectors, these corners, if you will, multiplied by these matrices. You can see what ends up happening to the shape. So also we get our transformations. So when we were thinking about all those transformations that were happening in pre-calculus 1, well, this is why it works out the way it does. We're discovering this is why it works out. So we have the transformation where we have a reflection across the x-axis. Notice where the negative is. It's actually down here in the bottom right. The reflection across the y-axis is actually up here in the top left. And then, of course, we can rotate the axes. Remember rotation of axes in pre-calculus 2? Here's our rotation of axes matrix, if you remember that from pre-calculus 2. And then, of course, we want to do a shear transformation. And so, when we have a shear transformation, the A is going to determine what the shear is going to look like. So visually, this is what's happening when we're doing linear transformations of matrices, using matrices as a linear transformation. Now, suppose we have this set S, this linear transformation defined from C3 to C4 is defined this way. I have x3, x1, x2, and x3. Now notice I'm going into a larger set. I started with a smaller set and I'm going into a larger set, and this is how I'm going to define it. So here is my definition. And if you want to think about this in terms of pre-calculus 1, we said here's f of x, and I'm going to do something to it. I'm going to do 3x plus 5, right? So I would have taken some value which would have been, say, 3, or actually let me use 5 or 4. And I would have done 3 multiplied by 4 and added 5 to it. and I would have had some output associated to the 4. So that's what this is saying. It says, hey, my input is actually a vector. I'm going to do some sort of transformation. I'm going to do some mapping. I'm going to tell you how to treat these values. And this is how you're going to treat these values. Just like here, I'm telling you to take your value, multiply by 3, and add 5. So just something to kind of keep that together. So here's how I'm going to define it. I'm going to say, okay, my C1 is going to be S of my unit vector in R3. And this is how I'm going to define it. I'm going to define it as 3, 1, 9, and 0. My C2 is I'm going to define it as my my unit vector with a linear transformation in E2. So, of course, the 1 is in the 2 position, and that's how I'm going to define that. And then, of course, I have S of E3, which is C3, is going to be defined this way. And so here's how we're going to define C. And by the previous theorems, we know that this matrix C is a linear transformation from S of X into C of X. So I started out with, you can see I started out with 3 entries and I ended with 4 entries. So I'm gone from C3 to C4. Now we've talked a little bit about pre-image and what that means. So let's do some pre-image work here. So suppose that T is the linear transformation of U onto V. And for each V, there is a pre-image of V. So in other words, for every V that I've got so every vector in this vector space V, I have a vector that was started out in my domain, that it was mapped to this V vector, and we call this the pre-image. So in other words, when I think about pre-image as being like your domain values and your image being your range values, if you want to think about it in pre-calculus 1, when we talked about domain and ranges of functions. So let's look at this linear transformation. So my linear transformation is, I'm going in C3, which means I have 3 entries that are complex, and I'm going to do the transformation so I end up in a matrix that is a 2 by 2, 2 entries, 2 rows. So then if I want to find 2 pre-images in the codomain, so in other words, I want to find out what could have been mapped to this V here. This is obviously in 2 by 2 matrix, and I want to figure out if there is any kind of matrix or any kind of entries that are mapped to that. So I'm going to just and I just chose this 2 by 2 matrix for no reason other than it's a nice 2 by 2 matrix. So I'm going to have my U1, U2, U3, and it's going to be in my domain. In other words, it's in my my pre-image of the linear transformation. So linear transformation pre-image. It almost looks like an undoing, like an inverse almost, right? Well, we'll talk about that later, what that means. And so what we end up with is this, that this is what V is. That means I've done some transformation of U to get V, which is this, which means I started out with U1, U2, and U3. Now, if I go back to the way that I defined my transformation up above, so here's how I define my transformation up above. And then I have my A and B, so my U1 and U2 are subtracted. And then when I do that, you can see I'm going to end up with 4 equations and 3 unknowns. I'm going to set this first equation here equal to this first position because they have to be equal. I'm going to do this second equation to this, and you can see that's this one. And then I would continue with this equation set equal to this, and then of course this final equation set equal to this, and I end up with this matrix right here. Here's the matrix I end up with, where I have the 1 and the -1 from this is equal to 2, and then the next line would have been 2, 2, 1, so 2, 2, 1 is equal to 1, and etc. If I do the reduced row echelon form, I get this. Now remember, this is an augmented matrix, and this augmented matrix tells me I have 1 free variable, because my pivots are in columns 1 and 2. I don't have a pivot in column 3. That means I have an infinite number of solutions, and that's because my number of pivots is less than the number of columns that I have as variables. So that tells me that if I look at the way that I would define my null space, if you remember my null space, it would have been, in this case, if I take a look at this first row here, I'm going to have x sub 1 plus 1/4 x sub 3 is equal to 5/4. So x sub 1 is equal to 5/4, that's this, minus 1/4 x sub 3, and you can see that's that. And then, of course, I would have done the same thing here, and I get this, which we know that the other way that we can write that is in this form, which we can write it in this form, which is this form here. So we know that this is a possible, one of many possible solutions because we have an infinite number of solutions. So these could have been possible pre-image values for that matrix that I chose. Now let's take a look at this matrix. Again, I'm just choosing random matrices that are 2 by 2. Some of them will work out nice, some of them will not. Let's take a look at this. We said the same thing as we did before. Now, this is a augmented matrix. Notice where my pivot is. My pivot is in the last column. That tells me we're an inconsistent system, which means there is no pre-image of this particular matrix. It may be in a 2 by 2 matrix, but there's no pre-image. In other words, I don't have anything mapped from U into V to get that matrix. So I chose 2, 1 worked out, 1 did not work out, and that's okay. Now let's take a look at the theorem of linear transformation on a basis. Suppose U is a vector space with basis U1 to Un, and the vector space V contains the vectors V1 to Vn, which may not be distinct vectors. They could all be the same vector. They could be different vectors. They can be distinct. Then there is a unique linear transformation that takes my basis vectors and turns them into my other set. Now this should sound very familiar. What we had done in the past is we said, here's my set S. Remember this? My set S, and I said, hey, I'm going to call this the span, and it was like U1. Actually, let me use V's. So let me do this. Let me use V's. And we said, hey, we had V1, and we had V2, and we had V3, and etc. And then we said, hey, can we find a basis? Is this the basis? And we found sometimes, no, that was not the basis because they were not linearly independent. Well, now we're saying if I have a basis here, if I have this basis B, then I'm going to be able to find a linear combination that's going to take my basis and get the vectors in V. So consider this linear transformation of C3 into C2 that is required to have these values, where I have T, my linear transformation, I have these 3 things going on. So I have my first unit vector, and I'm going to do some transformation. I'm going to end up with 2 and 1. I'm going to take my second unit vector, and it's going to end up, and these are the bases for C3, and it's going to end up in -4 and 1. And then I have my third unit vector in C3, which is going to be transformed into 6 and 0. So I'm going to do some sort of function, and these are going to be the outputs for it. So of course, here's my basis in R3. We know there must be a linear transformation that is going to take these into R2 or C2. So let me erase this. Okay, so let's just start with a vector W. Again, just randomly chosen. So we have 2, -3, and 1. So 2 times my unit vector, 3 times my unit vector, and 1 times my unit vector. Then if I do this transformation, it'll be 2 times what the unit vector would have produced when I did the transformation. I would have had -3 times the unit vector that would have been produced with my linear transformation. And then I would have had 1 times that linear transformation. Now all of these, I want to make it clear that all of these are coming from up here. This is this, this is this, and this is this. Now, when I do this transformation, you can see that I'm going to end up with 2 times 2, 2 times 1, negative 3 times negative 1, negative 3 times 4, 1 times 6, 1 times 0, and then I'm going to add across and I get 13 and negative 10. Now, if we do it again with another vector, we have 5, 2, and negative 3. So 5 times the first one, 2 times the second one, and negative 3 times the third one. I'm going to get this t of x being 5, 2, 1, and 1, negative 4, and 6, and 0, and I end up with negative 10 and 13. So in other words, t could be computed in similar manners, so that given a formula for the outputs of t, the requirements of t have to behave in a certain way, chosen by the basis of the domain, and that's all that has to happen, is that it has to behave that way. So let's kind of move on. Linear transformations of compositions. This is how we defined it, was we can do the composition. So we can first do the transformation on t, and then the transformation on u with the t transformation, and then get an answer and then do the composition. Now that if we think about that in a pre-calculus 1, that was something like f composed with g of x, that kind of thing. So this is showing us that this will work out when we're working with polynomials. So that's kind of nice. So suppose that this is our theorem that goes with it. Suppose that t is a linear transformation and s is also a linear transformation. Now notice that I'm going from one domain into a codomain. That codomain becomes a domain of my outer function, which I end up with in a brand new codomain w. And we know when this happens, it is a linear transformation. So let's take a look at this. We're going to define t as C2 into C4. And notice that if I do S, it has to match up with that domain, or that codomain size, because it becomes my domain on my outer function. And so I start out in C2, then I go to C4, and then I take C4 back down to C3. Here's how I'm going to define t, the transformation for t. Here's how I'm going to define the transformation of s. So doing the transformation of x1 and x2, then the first thing I'm going to do is I'm going to put x1 and x2 into this. So I get, these are my entries now. These are my entries into my s function, which gives me this. And then you can see I end up with in C3. So this is a linear transformation. We didn't have to prove it. We knew it was because it's a composition of 2 linear transformations by our previous theorem. And then the other useful outcome that we get for this section is if u and v are vector spaces, then the set of all linear transformations from u into v, linear transformation into u of v, is a vector space when the operations of those given in the definitions of linear transformation addition up above and linear transformation, scalar multiplication up above are used. So that's it. There's a lot in this section. We'll spend some extra time on it if you need, and then we'll go into the specific types of linear transformations. Now, if you think about it again, if you kick back to your pre-calculus 1 class, when we first learn the algebra of functions and the composition of functions, and then we went into doing one-on-one functions to find inverses, well, we're going to do something similar in this chapter, but we're going to be doing it with linear algebra definitions and such, which of course is how it kind of way that pre-calculus ends up working, is because of this class. The things we learn here is the foundations for why you can do that in your pre-calculus class. Anyways, that's it, and we'll see you tomorrow in class.